Hi, everybody. Welcome to Paleo Talks. I'm Dr. Blaine Schubert, coming to you from East Tennessee State University, the Center of Excellence in Paleontology, which oversees the Gray Fossil Site and its Natural History Museum. We are now on episode 11. This one is The Silence of the Allosaurus, our first time actually having dinosaurs as part of the program. And as you'll see, our guest here is coming from a background of crocodilians and then using that work to look at some of the bite function that goes into feeding behaviors and looking at dinosaurs and looking at crocodilians. So the silence of the Allosaurus, scavenging and cannibalism among late Jurassic theropods. We have Dr. Stephanie Drumheller-Horton. And in this program, we're going to, just like we've done in previous weeks, we're going to go through the first part, and then we're going to lead into questions from the audience. David, if you wouldn't mind just going into a little bit more of how the structure works. David is our co-host.
Sure thing. I'm David Moscato, one of the Gray Fossil Site paleontologists and science communicator. So the way this is going to work, we are streaming live to YouTube as we had the last couple times. Blaine is going to talk with Stephanie a bit about this research, and then about halfway through, so 20 minutes in or so, we will open it up to questions from the audience. So if you are following us on the YouTube video, there is a live chat. So start putting your questions in there once question time comes along, and we'll read them out. If you're having any trouble accessing the YouTube chat for whatever reason, send us and you have a question you want to ask, go to the Gray Fossil Site Facebook page or Twitter account, send us a message there. I'll keep an eye on it so that I'll spot questions coming in there as well. And then we'll take questions for a while.
All right. Without further ado, we have Dr. Drumheller. She is a faculty member in the Department of Earth and Planetary Sciences at University of Tennessee, Knoxville. So go ahead and take it away, Stephanie, and show us some of this amazing material.
All right, let me get my slides up for you.
Actually, can we see her, David? Make sure that she's on there too.
Yep, you are spotlighted now.
All right. So you already read my title, so I'll dive right into it. This research really started with me looking at bite marks in crocodilians. There's a long history, particularly in anthropology, so study of humans and ancient humans, looking at how mammalian predators modify bones. But there hasn't been as much work looking at non-mammalian predators. So back in graduate school, that seemed like a good thing to try to address. So I was essentially taking scraps from butchers and going down to the St. Augustine alligator farm in Florida, and I would take that material and I would throw them into the enclosure with all these different species, and then we'd get them back again. And that was, of course, a little bit more exciting part. And then we'd bring them back and clean them up and look at the marks and see, is there something about these bite marks that we can identify them, that we can tell them apart from other groups that might have been leaving marks on bone in the fossil record? And fortunately, it seems like yes, the dentition is somewhat reflected in the marks that they make. So we're actually getting pretty good at identifying crocodiliform bite marks in the fossil record. And I ended up looking,
if you wouldn't mind, could you go back to the intro slide just so that you can tell the audience about the title itself?
That would be a Hannibal Lecter reference. So that was one of the things that we found at the end of the story. So when I started taking my modern samples and looking at dinosaur bite marks, is that we had several different big theropods who were very clearly eating each other at this site in Colorado. So
perfect, thank you.
Yep. Sorry, jumping ahead of myself. But no, most of my work, I've been looking at sort of the crocodiliform. So you take your group that's bracketed by all the modern species, and then crocodiliform is their closest relatives, a little further down the family tree. So I pulled this one up. We promised dinosaurs. Most of my previous work with dinosaurs was actually crocs eating dinosaurs. So these are bones from a small, juvenile hypsilophodontid that this one was easy for me. I felt like I was cheating because right there, that's actually an embedded tooth. So I get called in to look at this and I'm like, there, that did it. My job is done. But no, obviously it was a bit more than that. So we see marks like this. That's, obviously the fossil, but down here is one of my modern cow bones with alligator bite marks on it. We call this a bisected mark. So crocodilians, the stereotypical croc tooth is conical, and you have a ridge called a carina that as the tooth gets worn before it falls out, it sort of chips away. But in the freshly erupted teeth, it'll make almost a sub-score within the larger bite mark. So it's very characteristic. And we found it here from a croc on a dinosaur. So putting them in their proper relationship with this clearly superior clade. I'm not biased at all. And I have started venturing out of my comfort zone. I probably should have put a picture in here. I had a paper come out recently that was actually looking at bite marks on a data logger in a conservation project in Florida, where they were putting nest data loggers in American crocodile nests. And they kept losing data loggers, and they weren't sure what was going on. And then they finally found one that had just been smashed to bits and was covered in bite marks. It's like, I think I know your problem. So, but this was maybe my first step away from just crocodiliforms, but we're still on the Pseudotsuchian side of things, so the croc side of the Archosaur family tree. This is actually a thigh bone, a femur from a Rawasuchian, so something that looked kind of like that. And you can see a bunch of the marks here, but the one that caught our eye was, again, I get spoiled. I keep finding these embedded teeth. So we were actually able to CT scan that and then section it out and figure out that it came from a phytosaur. So phytosaurs are not particularly closely related to modern crocs, but if you saw one from a distance, they have a very similar body plan. So they were probably doing something similar in their environment. So we were able
that's
to.
What we have. That's what we have at the top here.
No, that's the victim, I guess you could say. That's a Rawasuchian. So that's who this came from.
If you didn't have that embedded tooth, you wouldn't be able to say as much, I suspect.
It would have been a lot harder, because one of the very interesting things about this specimen is that it was healing. So you have that embedded tooth, and there's actually reaction tissue all the way around it. There are a couple other marks sort of along the line of the tooth row. So they would have happened during the same biting event from different teeth. One of the teeth got left behind, the others left. So the original shape of the marks that would have helped us figure out who the actor was had actually been obliterated by the healing process. So without that tooth, this one would have been really tough. Some of the other ones were actually, I can't really say fresh. We're talking about a Triassic bone here, but they didn't have any evidence of healing associated with them. So this animal clearly, went around with this tooth stuck in its hip for some time. But then either at its death or afterwards, somebody else came along and munched on it too. Okay. So my friend and colleague, Julia McHugh, got a position a few years ago at the Dinosaur Journey, which is part of the Museums of Western Colorado. And we knew each other from graduate school, so she knew what I was up to and what I did. And she said, well, I don't think I have croc bites. I have dinosaur bites, though. So they were known from the site. But when she first got into this position and started looking around in the collections, she contacted me and said, we have a lot, like a lot more than expected. And this is one of the more obvious sort of in-your-face examples that you can look at. It's on a sauropod that's actually on display if you ever visit. This is in Fruta. So it was a sort of dream, I guess, project for a taphonomist, because Julia has listened to me gripe for years, we're gonna go with years at this point, about how the way we collect fossils affects our ability to do certain types of studies with bone surface modifications. And I mean, I'm not criticizing a single sauropod. They're big. I mean, that takes up a lot of room in collections. It takes a lot of effort to bring them in from the field. You have to put them somewhere. You have to hire people to then take care of the collections. So we usually pick and choose what we bring back from the field. And a lot of times that comes down to the pretty stuff. So we bring back preferentially things that are maybe going to be taxonomically more informative. We're more likely to be able to identify them. But that's not what I'm interested in. I'm interested in messed up bones. So I guess I would describe myself primarily as a taphonomist, and I'm most interested in bone surface modifications. So Julia it was like a three wishes from a genie kind of situation. She's like, if you could do any kind of project with this, how would you dive into it? I said, collect everything, absolutely everything. Because it used to be, again, they would preferentially bring back the complete stuff, the more identifiable stuff. So she would put out these buckets. They nicknamed them nugget buckets, which apparently all of her volunteers thought was delightful. And if it was, I think our final cutoff was 2 centimeters in diameter in any direction, it went in the nugget bucket. So we were bringing back lots of fragments of things that were identifiable as bone, but who they belong to, I came up the first time and I held a big training session for everybody who was working on the collection. We have 2 student interns, Miriam and Anya, that I'll show you pictures in a minute. All of working and volunteering in the labs, sort of train them on what to look for. And then I got to go through the collections too. So that's me way up a ladder looking at some of their material in collections at Dinosaur Journey. And it was sort of the funny thing is I got to go up a couple times and it was always sort of the red carpet treatment because all of these people that I had then trained were the ones going through the collections and finding stuff. So when I show up, it's like, here's all the cool stuff we've already found. So I got to just go in and play with that. I did go through plenty of the cabinets, myself too, and especially when we were finishing things up. But these are pictures of Miriam and Anya actually doing some surface scanning. We have digital copies of some of the more interesting marks, looking at those. So they were absolutely instrumental to this whole project. What was kind of weird was how many bite marks we were finding. So there have been, obviously, I love how gory this picture is. It's another
Now, who is the artist?
ridiculously gory. There's a lot of prior research looking at theropod bite marks on bone, but usually it's sort of incidental. Somebody was digging around in collections looking for something else and just happened to notice, hey, there's some gouges on this bone. I wonder what's going on. So there have been some previous studies that have said that dinosaurs maybe were a little bit weird with how they use bone as a food resource. So the previous prediction was that you would expect fewer than 5% of the bones in your collections to actually have marks on them. And this, you draw some parallels with groups today like Komodo dragons. My co-author on this project and colleague, Dominic Diamore, had done work with modern Komodo dragon bite marks, just like what I had been doing with crocodilians. And with these monitor lizards, they don't seem to be actively seeking out bone. They actually seem to almost be dodging it. So when you get bite marks, they're sort of accidental. They didn't mean to. So maybe that's what these theropods were doing. They weren't seeking out bone as a food resource. They were eating the meat, and any bite marks we find underneath were just sort of a happy accident for us to find. When all was said and done and the smoke cleared, we had looked at over 2,000 bones, and about 30% had bite marks on them, which is bonkers. That's up in the sort of predicted range for mammals. And many mammalian predators that those studies are based off of do actively seek out bone as a food resource. So you think about groups gnawing on bones, hyenas being maybe the extreme end of that, but other mammalian predators as well. So then we started asking, what's going on here? Why do we have so many? And we sort of boiled it down to 2 possible explanations. The first one was maybe we were looking at this problem of collector bias, because bulk collection in dinosaur sites, that's like a unicorn. I mean, that almost never happens. So we had this problem where doing apples to apples comparisons to previous dinosaur studies is really difficult, because we don't know how those collections were assembled. And we suspect that it might have been, again, preferentially bringing back the more complete stuff. So maybe our collection protocol led us astray. Or maybe there was legitimately something weird going on at the Myget Moor quarry. So this is actually a photograph of the quarry itself, so just to show where the fossils come from before we dig into what this site would have looked like back when these animals were running around. So hypothesis 1, this is totally normal. This is just how dinosaurs actually did, and our collection protocol has messed us up. Option 2 is something odd was going on, and these animals were having to more completely process skeletons, prey items, than they would under normal circumstances. And we do have some support for that, both in our interpretation of the environment and also from the bite marks themselves. So during this chunk of time, we're talking about 150 million years ago during the Jurassic, this part of Colorado would have a wet and a dry season. So during the wet season, the water table would rise and you'd have these watering holes across the landscape. There wasn't any permanently standing water. There weren't anything like rivers in this particular site. So in the dry season, the water table drops. And it's possible that what we're seeing are groups that are coming through and scavenging just any food resource they could find during hard times. So in other Morrison Formation sites, we do have good evidence for things like severe droughts and fires. So the environment, it definitely had some moments where it probably wasn't that great. And in modern settings, we see if you have these resources lying out on the landscape, groups that we think of as predators have no compunction about scavenging. They do it all the time. It's a free meal. Why would you waste the calories hunting something down if a free meal is just waiting on you? We do suspect that we have a lot of evidence for scavenging here because we kept finding bite marks like these on what we would call low economy bones. So if you're finding lots of bite marks on things like toes and fingers, you're probably late to the party. That's not the first place a carnivore goes. They're going to go for the greatest bang for their buck. How much food can I eat? So usually you see them targeting things like the torso, the viscera, and then the larger long bones of the limbs where you have these large attached muscles coming in. But if you're finding little bite marks on toes, like in this photograph, that's probably the last thing that was coming along, and you're just eating anything that's left on that carcass. And there's a lot about the taphonomy of the site that lets us know that these remains were lying around on the landscape for a really long time, months, if not longer. So we joke constantly that it just had to smell terrible. But these predators are coming through, they're chewing on stuff. This is actually one of our examples where you can see the little striations. So theropod teeth are serrated, just like a steak knife. And those little serrations can leave individual grooves. And it's one of the reasons why I called my buddy Dominic and said, hey, come help us, because he had developed a technique to use these striations to actually get some body size estimates. So how big was the animal that left them behind? Because we were trying to narrow down who our potential actors were. The overwhelming majority of the theropods from Myget Moor are Allosaurs, but we do have an extremely small number of ceratosaur bones known from the site. And if you go to other Morrison sites, you have other theropods as well. So most of these marks turned out some results that were right within that Allosaurus ceratosaur range. But we got one that was a little bit weird, but kind of fun, a little bit of a mystery. It was bigger than anything that's known from the site. And I'm not a dinosaur taxonomist, so I'm gonna step away from this fight slowly and try to not make any sudden gestures. But there are some remains of an animal that would have been about the right size, known from a different Morrison locality, that depending on who you talk to, it's either a really large allosaur or it's a separate group called Saurophaganax. There are a couple other big theropods. So we have this indirect evidence that somebody in that size range was knocking around Myget Moor, even though we haven't found them. But from just the sheer number of marks that we have, including on other theropods, so other allosaurs, we're pretty certain we're looking at the first evidence of cannibalism in Allosaurus, which I wouldn't say that that's necessarily surprising. Many modern carnivores are cannibals. What's surprising is actually finding evidence for it. I was drawing a comparison between them. Nobody's surprised that dinosaurs have skin. Everybody's surprised when we find the skin. So this is only the third group of dinosaur that we have direct evidence for from the Mesozoic for cannibalism. Tyrannosaurus rex, we have an example up here, and Majungasaurus, we have direct evidence for this. So this is the third. Usually people ask me, but what about Coelophysis? And that turned out to be an accident. They have a really beautiful specimen with gut contents, and the bones that were in the torso were originally identified as juvenile Coelophysis. but some subsequent research by Sterling Nesbitt and colleagues, they came back and said that is not a coelophysis, that's actually a croc relative. So we dragged coelophysis' good name through the mud. So this is actually the only third time that we've been able to say, yep, we have direct evidence of this behavior in these dinosaurian groups.
In modern crocodilians, I'm guessing
Oh gosh, yes.
Yeah, they're happy to eat each other.
Well, it's also, we love putting behaviors in boxes. So we love calling groups predators or scavengers, and then, I don't know, pretending to be shocked when the animals don't care about our boxes and blur the line between the two. So
Sure.
Plenty of groups that we think of as scavengers will hunt. Plenty of groups that we think as predators will scavenge. And lots of groups will fight each other. And if your opponent in that fight happens to die in the process, well, now you have some convenient food. And that happens all the time in crocodilians. They fight constantly and have whatsoever about eating each other when that happens. So again, it perhaps wasn't terribly surprising that we found this, but it was surprising that we actually got the evidence for it. And that's where our picture here comes from that Brian Ang made for us. So most of the animals that you see are allosaurs in this, but we do have a ceratosaur who's, I don't know, taking exception to somebody stepping in on his dinner. Because it's roughly what we think was going on. We were looking at this sort of as an analogy to some of these videos that you might see of hyenas and lions and other predators and scavengers coming in and eating prey, this sequence you get of different predators interacting with a single set of remains in modern settings, because it seems to explain what we're finding at this Morrison site actually really well. What we're really hoping to do next is, as I said, we have this problem of comparing this to other sites because we did this, for dinosaur research, really weird bulk collection strategy. So we're trying to go and bribe and swindle and sweet talk some other paleontologists to, at least for a little while, do some bulk collection so we can compare to some of these other assemblages and see. Because right now we simply don't know. This could be completely normal and just how groups were during the Morrison, or there might have been something really weird going on at Might Moor, and we're basically seeing animals getting kind of desperate and eating really nasty stuff when maybe they wouldn't have normally.
Right. What about what's coming out the other end? I know in crocs they typically fully digest what they're eating, and you just don't really get bone preservation coming out. But what about this site and these types of sites? Do you ever get coprolites that still have bone in them?
This site, we don't have coprolites to go along with this. The exposure times that we're looking at, usually coprolites need sort of more rapid burial and maybe a lower energy system. I will say that we do have theropod coprolites. Probably one of the more famous ones was published by Karen Chin of T-Rex. And T-Rex is, it has been interpreted as a little bit more of a bone crusher. So some research with, we were talking about Paul Gienack and Greg Erickson and bite force studies. So looking at bite force in T-Rex, it would have been extremely high. And if you partner up that information with the T-Rex bite marks we have with this gigantic coprolite that Karen Chin described, it definitely paints a picture of a bone crusher. And the really cool thing about that coprolite is in some modern groups, if a predator gorges, if they just eat a whole lot in one setting, a lot of it's sort of inefficient. A lot of that material makes it all the way through the digestive tract, and it's not very highly modified. So in big cats, there are actually examples of like entire digits of prey animals that are still, the bones are all together, the skin is still on the outside because they just ate so much and it passed through without being digested. In this coprolite, they have lots of bones, but they also have soft tissue preservation. Coprolites are actually kind of amazing. They're sort of weird little micro preservational environments, and you get stuff preserved in them that you might not necessarily elsewhere, even in the same horizon. So we do see this in other groups, but I can't talk about Might Moor ones because it wasn't the right type of system to preserve coprolites. I would love to. I'm just barely starting to play with coprolites. I have a site in Texas that I have a few hundred of them back at the department waiting for us all to be able to go back. to sort of dig into, but
And
it's certainly the other end of the equation.
Are you starting to see some real patterns in some of these different theropods? You mentioned, the striations on some of them, conical versus V-shaped. Are those patterns that you see?
Yes. If you have sort of extreme adaptations of the teeth, so in Tyrannosaurs, you get some of the teeth being almost D-shaped, and people call them killer bananas, so you get much wider impressions from them. I do love that because they do look like bananas, but if you have a much more slender tooth, you're going to have a much more slender mark. The reason that we were looking at the striations with Dominic's data set is because that does seem to change with body size. Now, there are a couple of groups that got kind of weird with it, and the spacing of the denticles on their teeth broke with the usual pattern, but for most of these groups, it seems to be a pretty good relationship. But then you get into the issue of it can only ever provide a minimum body size estimate, because if you think, like, if that's the tooth and these are the serrations, if you drag perfectly across the surface of the bone, you're going to reflect the accurate spacing. But what if the tooth is moving like that? It'll make them look closer together than they actually were. So you can never, I guess, really overestimate the size of these groups from those striations, but it's extremely easy to underestimate. And striated marks are really ridiculously rare. So if you're looking at a dinosaur assemblage where you would expect fewer than 5% of the bones to have any marks on them at all, Dominic's research with Komodo dragon says take that 5% and then take 5% of that might actually get these marks preserved. So the fact that we had hundreds of bite marks to look at, we were sort of spoiled. It was an embarrassment of riches.
It sounds like the record is really biased out there.
I think so. I rather suspect that if we can get a project going and looking at a bunch of other sites, we're going to start finding more. And part of this is just it's just search pattern. So you train as a paleontologist to look at your thing that you work on, and it's funny because I have a completely unrelated project. I went to East Africa this last summer with Chris Brochu to look at some Pleistocene crocodilians that are in the human, sort of early human relative sites. And of course, you've got hominids coming out of there, so everybody is laser focused on them. But there's also a lot of croc material there as well. And there are a couple hominin specimens that have croc bites on them. So clearly this was a thing that was happening. So that's why I went over. And it's funny because, Chris is focused on croc anatomy and what are the bones doing and what are the bones looking like. And I am looking at how are the bones messed up? How are they not normal? So I come in, and the first day we go to collections in Ethiopia, and I'm like, somebody bit that one. And it's just, that's not what he was looking for, so he hadn't noticed it. And by the end of it, it was popping out to him too. So again, I mean, we have evidence for crocs, biting each other on the face all the time. So,
well, we better head over to questions that are coming in. David?
Yep. So as a reminder for anyone who is listening and who is here in the chat with us, if you have a question, we'll start taking them from the audience. So if you're here with us in the YouTube video, type your question into the YouTube chat. If, as I said before, you're having some trouble getting your question into the YouTube chat, hop over to the Gray Fossil Site Facebook page or Twitter account, and I'll keep an eye there for questions as well. We do have a question from user Attila the One, who has asked, using the striation technique, how are you able to differentiate between Ceratosaurus and Allosaurus marks? Now, if I understand correctly, Stephanie, you weren't able to differentiate.
Except for that one that was big enough that we could exclude the Ceratosaurus. So they are similar in body size, especially when we were getting slightly smaller estimates. So things that were maybe not a completely full-grown Allosaur, not a completely full-grown Ceratosaur. So for most of them, we couldn't tell them apart. And then we had that one odd outlier that spat out a body size estimate that was just, it was too big to be a Ceratosaur. And then we get into the fuzziness of what even is Saurophaganax, and maybe do we have some of these other very large theropods at the site. But again, it's also extremely likely that we're just looking at an exceedingly large Allosaur.
Right. And here's a follow-up question from me while we're waiting for more people to send in questions. Did you also find smaller bite marks? Bite marks that were...
Oh gosh, yes.
Okay, I would have been surprised if you hadn't.
No, and I think that's also part of what was probably running our numbers up so much more, because the really obvious ones, like huge gouges, like I showed you in that very first picture that Julia first shared with me, those are kind of in your face. They're hard to miss. But the smaller bites, one of the tricks that we use is, we call it, when you're writing your very fancy methods section in the paper so to be palatable for publication, we call it raking light. In practice, you basically take a flashlight with you into collections and you're shining it sort of along the surface. These things are an absolute nightmare to photograph, because usually if you shine light just straight down on the surface, all of that texture will almost disappear in the flash of the camera. So you have to set up the lights at an angle that are catching all these bumps and grooves. But go into collections with a flashlight and you start holding it at a very low angle over the surface, these different textures really start popping out and becoming a lot more obvious. But again, I mean, how often do you get to train up 2 interns and then let them just unleash themselves on a collection for 2 solid years? Because that's what it took. I mean, going through thousands of bones this way, it takes a while. So
it's amazing how just looking at something in different light, I mean, it can change the way that you'll see the taphonomy. And it's the same way with trackways in caves, that if you're walking with your headlamp on at your eyes, then you're not going to see trackways very well. But if you turn off your light and have somebody else shine the light across, then you're going to have that jump out at you, that relief pattern.
It's funny because I gripe about this so much, but taking photographs for publication, it just makes you want to scream, because something that's really obvious when you're holding it in your hand and then you get it on the other side of a camera lens and you just can't get a picture to show it.
So we've got a couple more coming in.
Okay.
Now we talked in this presentation so far, Stephanie, that you've historically worked on crocs, and this research is on dinosaurs. Raphael is asking, would it be possible to tell if pterosaurs scavenged by looking for bite marks?
Possibly. You have the tooth groups and the ones with beaks. We do have a little bit of modern forensic research on, I guess, beaked animals and the marks that they leave on bone. A lot of them are sort of ephemeral, so they might be something that you could identify in a forensic context, but you might not expect to end up in the fossil record. But there are examples of, say, the crowned eagles that eat a lot of primates. Some paleoanthropologists were particularly looking at those groups because there's a very famous early human relative fossil called the Tong child that is missing a chunk out of the back of its skull, and there are a lot of gouges with this sort of triangular, very sharply V-shaped cross-section. And it's been interpreted that maybe this young individual was actually eaten by a bird. And there were certainly birds that were big enough, and this was a small enough species that it's not outside of the realm of possibility. So we do see these triangular punctures associated with claws, and then these sort of slicing V-shaped structures that you can get with beaks. So I have never seen one. But especially then going back to groups with teeth, I would expect it's entirely possible. It's just not something that I've dug into yet. We'll go with yet. Maybe one day.
You're working your way through archosaurs. It's only a matter of time, I guess.
So. I'm definitely getting weirdly out of my comfort zone in the last year, because I had the bite marks on the data logger, which was PVC. And then the other paleontologist that I work with sometimes at UT is Colin Sumrall, and he works on Paleozoic echinoderms. And he comes to my office one day with this handful of blastoids, and he's like, "Do those look like bite marks to you?" Yes. So now I'm working on fish. That's definitely out of my comfort zone, but.
Well, back on dinosaurs, we've got a question from Tasha, Mammoth Site interns here. they say. Hello, Mammoth Site. One of our questions is, how do the Allosaur bite mark percentages on collected bones compare to Tyrannosaur bite mark percentages?
Again, it hasn't been as widely reported. So a lot of, at least as far as the studies that I'm familiar with, the Tyrannosaur bite marks that we have several, but they seem to be, again, these sort of incidental, hey, I found this stuff, let me describe it from this collection. As far as looking at these site-wide percentages, these site-wide surveys, there was one other study from a dinosaurian site in South America, but even that one, it wasn't reporting frequency. It was just, it was reporting just occurrences. So this type of study, this type of site-wide bone surface modification survey becomes a lot more common in Cenozoic deposits, and groups like zooarchaeologists and paleoanthropologists do it all the time. We just don't have a data set as a good comparison point right now within Mesozoic sites. We want to make them, or we would like to convince other people to make them, but we just don't have it available. I would strongly suspect, especially with things like the coprolites, that secondary evidence that T-Rex is definitely chomping up bone, I would expect it to be really common. I would expect there to be just tons of bite marks, but if we're not collecting the fragmentary, busted up, ugly stuff, then maybe we're underreporting it.
Gotcha. Let's do this one more question, and then we can go ahead, as is tradition. What we'll do, everybody who's watching, is we'll end the recording, but if people still have questions, we'll keep taking questions after the official presentation has ended. So this last question, also from our Mammoth Site interns, besides the selective bite marks at this site, the Megatmore Quarry, what other evidence indicates the event of a severe dry season?
At Megatmore, that's not where a lot of this is coming from. We see evidence for big droughts and fires at places like Cleveland Lloyd. It's actually part of the reason that we were really excited to work with Brian Eng on this artwork is that he's been making videos with the Cleveland Lloyd guys where they're the ones pulling out this evidence for drought. So Megatmore, it's just we're in the same formation. It's all Morrison, but for right now we don't have that same direct evidence in the rocks.
All right, great.
Well, I feel like before we say no, I do want to thank all of the volunteers. That's one thing I always try to give them a shout out, because the Dinosaur Journey site, most of these fossils were not dug up by paleontologists. They were dug up by members of the public. So you can actually sign up with the museums to go out and volunteer. So a lot of these things, obviously there's a paleontologist on site sort of directing traffic and giving instructions, but the majority of this stuff was dug up, it was prepared, it was brought back to the labs by just citizen scientists, volunteers, and members of the public, which is another thing that I think makes this site really cool. So
yeah,
very cool.
Before you stop recording.
Very cool. One of the things I wanted to mention too that we didn't really get into, and some people might not realize, is the tooth replacement that you have in this group. And speak to that for just a minute, and sort of the advantage that you have as a theropod in this case.
So, we're mammals, so we think it's normal, but it's not, having just the two sets of teeth. And we've had this sort of trade-off where you look at mammalian teeth, and we tend to have really thick enamel, because once you get those adult teeth, those have to last. We cheat because, tools and dentures, but other mammals, once you have those adult teeth, that's it. And if you lose all your teeth, then it's going to make things a little bit harder. But you look outside of our lineage, and groups like crocs and groups like dinosaurs were constantly shedding and replacing teeth. And some of them, we have some evidence from the bones that they were doing it actually quite rapidly. So chomping into bone, that's something that we might be a little bit leery of, because you don't want to crack your tooth. That's
right.
Your only tooth. But for these guys, it was less of an issue. If you wore a tooth out or you damaged it, then who cares? It's going to fall out and a new one's going to come in right behind it. So it does definitely affect how they're interacting with prey, how they're behaving, and then eating stuff once it's actually killed.
Right. And so going along with that, I think you're right. I think that we're just not seeing a very complete record here in terms of the bite marks at sites, and the fact that they would lay out on the ground longer and not be in really great depositional environments. You're probably going to go way higher than the mammal record when it comes to bite marks eventually.
It's possible, but I mean, there are plenty of mammalian groups that will absolutely wear a skeleton out. So you look at modern hyenas, and if they are left alone with a carcass for too long, you have unidentifiable munched up bone shards.
True.
That's pretty much it.
All right, well, we better wrap it up. If there's anything else, Stephanie, that you wanted to throw in there, but again, thanks a lot for coming on to the show. That was exciting. Definitely had a lot of viewers this time.
Well, thanks for having me.
All right.